November 11th, 1944, 11,000 feet above Ormoc Bay, Philippines. Commander David McCampbell advanced the throttle lever of his F6F Hellcat past the metal detent that every pilot had been warned never to cross except in the most desperate circumstances. The wire snapped. A small green light illuminated his instrument panel. Behind him in the fuselage, a pump activated with a mechanical whir, forcing a mixture of water and methanol toward the massive Pratt Whitney R-2800 engine. The aircraft surged forward as if kicked from behind. The climb rate indicator needle swept past 2,500 feet per minute through 2,800, settling at nearly 3,000 feet per minute. Below him, 3,000 feet lower, a Japanese Oscar fighter that moments before had held the altitude advantage was rapidly becoming irrelevant. In 3 minutes of sustained climbing, McCampbell had erased the enemy's position, gained firing superiority, and demonstrated the effectiveness of a system that pilots called war emergency power. What they did not yet fully understand was that this emergency system, built into every F6F and late production F6F Hellcat, represented one of the most significant but least celebrated tactical advantages American pilots possessed in the Pacific War. The Japanese never developed anything comparable. They never understood why American fighters could suddenly accelerate and climb at rates that defied the published performance specifications captured from downed aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of war emergency power begins not with a desperate innovation during combat, but with a calculated engineering decision made in conference rooms in Bethpage, New York, and Washington, D.C. during 1942 and early 1943. The United States Navy faced a problem that could not be solved through pilot skill or tactical doctrine alone. Japanese fighters, particularly the Mitsubishi A6M0, could outclimb American carrier fighters in almost every engagement scenario below 14,000 feet altitude. The Zero achieved this through ruthless weight reduction. The A6M carried no armor plating protecting the pilot. The fuel tanks were simple aluminum containers with no self-sealing capability. The airframe skin measured barely 0.03 of an inch thick, thinner than heavy cardboard. Every gram of excess weight had been eliminated to create a fighter that weighed just 5,555 pounds fully loaded, nearly 2,000 pounds lighter than American fighters. This weight advantage translated directly into climb performance. At 10,000 feet altitude, the Zero could climb at 3,050 feet per minute, according to captured technical manuals tested at Naval Air Station Patuxent, River. The Grumman F4F Wildcat, America's primary carrier fighter in 1942, struggled to achieve 1,500 feet per minute under combat conditions, with full fuel, ammunition, and armor weight. The mathematics were brutal and undeniable. In any engagement where altitude determined survival, Japanese pilots held the advantage. American pilots learned quickly that attempting to climb with a Zero meant death. The tactical doctrine distributed fleet-wide after the Battle of the Coral Sea in May 1942 was explicit and unambiguous. Never attempt to outclimb a Zero. Never attempt to turn with a Zero at low speeds. Use superior diving speed to attack and escape. Maintain altitude advantage at all costs. If you lose the altitude advantage, run away. These tactics kept pilots alive, but they ceded the initiative to the enemy. Japanese fighters could choose when and where to engage. American fighters could only respond reactively, always on the defensive, always, seeking to escape rather than destroy. The frustration among Navy pilots was palpable and growing. They needed fighters that could compete on more equal terms. Grumman Aircraft Engineering Corporation had been working on the F4F's replacement since before Pearl Harbor. The company understood clearly that matching the Zero's maneuverability through weight reduction was impossible within American design philosophy. The Navy's Bureau of Aeronautics insisted that fighters carry armor protection for pilots, self-sealing fuel tanks to prevent catastrophic fires, and robust structure capable of surviving combat damage and rough carrier landings. These requirements added thousands of pounds that could not be eliminated without abandoning the principles that kept American pilots alive. The Zero's lack of protection meant Japanese pilots died from damage that American pilots routinely survived. A single .50 caliber bullet through a Zero's fuel tank created an inferno. The same bullet through a Hellcat's self-sealing tank caused a manageable leak. American pilots shot down multiple times returned to combat. Japanese pilots shot down once were usually dead. In a long war of attrition, protection mattered more than performance. But protection came at a cost measured in climb rate and maneuverability. Roy Grumman and his chief engineer, William Schwendler, concluded that the only solution was overwhelming engine power. If the aircraft would be heavy, it needed an engine powerful enough to move that weight with performance matching or exceeding Japanese fighters. The Pratt Whitney R-2800 double wasp radial engine seemed ideal. This massive power plant featured 18 cylinders arranged in 2 rows, air-cooled for reliability, with a 2-stage 2-speed supercharger for high-altitude performance. The base R-280010 engine produced 2,000 horsepower at military power settings, more than double the Nakajima Sakai's 940 horsepower that powered the Zero. Initial calculations suggested this power advantage would give the new fighter, designated F6F Hellcat, performance competitive with Japanese fighters despite the weight penalty. The first F6F3 prototype flew on July 30th, 1942, powered by the R-280010 engine. Test pilot Robert Hall reported excellent handling characteristics, solid construction, and impressive speed. Maximum velocity reached 375 miles per hour at optimal altitude, faster than the Zero's documented 331 miles per hour. But the climb rate disappointed Grumman's engineers and worried Navy observers. At sea level with full combat load, the F6F3 climbed at approximately 2,300 feet per minute, better than the Wildcat, but still inferior to the Zero's 3,000 feet per minute. At 10,000 feet, the F6F climbed at 2,360 feet per minute, still trailing the Zero significantly. Above 14,000 feet, the Hellcat's supercharger advantage finally gave it superior climb rate, but most Pacific combat occurred below 10,000 feet, where Japanese fighters retained the advantage. The Navy accepted the F6F3 for production in October 1942, despite these limitations, because it represented a substantial improvement over the Wildcat and could be manufactured quickly in large numbers. The first combat-ready squadron, VF9, received their Hellcats in February 1943 and deployed aboard USS Essex in March. They first encountered Japanese aircraft in August 1943 during operations in the Solomon Islands. The Hellcat proved effective, but not dominant in climb performance. Pilots reported that Japanese fighters could still outclimb them from low altitude if given any initial advantage. The tactical doctrine remained essentially unchanged. Use diving speed and superior power at high altitude. Never get drawn into slow-speed turning combat or climbing contests from disadvantaged positions. These tactics worked effectively enough to achieve favorable kill ratios, but they remained fundamentally reactive rather than proactive. Meanwhile, Pratt & Whitney engineers in Hartford, Connecticut, had been developing an enhancement to the R-2800 engine that promised significant short-term power increases. The concept was neither new nor revolutionary. German aircraft manufacturers had been using similar systems since the late 1930s. British engines incorporated comparable technology. The principle was straightforward and based on fundamental thermodynamics. Internal combustion engines generate power by burning fuel mixed with air inside cylinders. The explosion pushes pistons that turn the crankshaft. Maximum power is limited by how much fuel-air mixture can be compressed into each cylinder before ignition. The denser the mixture, the more powerful the explosion, the greater the power output. Superchargers increased power by compressing incoming air, forcing more oxygen into each cylinder. But compression generated heat, and excessive heat caused pre-ignition, where the fuel-air mixture exploded before the spark plug fired, destroying the engine within seconds. This phenomenon, called detonation or knocking, set the absolute upper limit on how much boost pressure a supercharger could safely provide. Higher boost meant more power, but also more heat and greater detonation risk. Engineers needed a way to increase boost pressure while simultaneously controlling the heat that boost generated. The solution was elegantly simple in concept, but complex in implementation. Inject a fine mist of water directly into the supercharger intake. As the water evaporated in the compressed air flow, it absorbed enormous amounts of heat through the thermodynamic process of phase change from liquid to vapor. This cooling effect lowered the temperature of the compressed air entering the cylinders, allowing significantly higher boost pressure without detonation. The cooler, denser air mixture could burn more fuel, generating substantially more power for a limited time until the water supply exhausted. Pratt Whitney designated this system ADI, an abbreviation for anti-detonation injection. Other manufacturers called it water injection or water methanol injection, because the fluid was actually a mixture of approximately 30% water and 70% methanol alcohol rather than pure water. The methanol served multiple purposes. It lowered the freezing point of the mixture, critical for high-altitude operations where temperatures routinely dropped far below zero. It provided additional anti-knock properties beyond water's cooling effect, and it added slightly to the fuel value, contributing a small amount of combustion energy. The complete system consisted of a tank holding approximately 12 gallons of water methanol mixture, an electric pump, pressure lines running from the tank to the supercharger inlet, an injection nozzle that atomized the fluid into fine mist, and electrical controls integrated with the engine management system. The tank was located in the fuselage behind the pilot's seat, as far from the engine as possible to minimize heat effects on the fluid. The pump was designed to activate automatically when the pilot advanced the throttle past a preset limit. A brake wire or mechanical detent prevented accidental activation. Once activated, the pump forced the mixture forward through steel lines to the supercharger, where it was injected as atomized spray into the compressed airflow. The engineering challenges were substantial. The injection rate had to be precisely calibrated to match engine RPM and throttle position. Too little water meant inadequate cooling and detonation risk. Too much water meant the mixture became too lean to burn efficiently, causing power loss or engine failure. The nozzle design was critical to creating properly sized droplets that would evaporate completely before reaching the cylinders. Too large, and liquid water entered the combustion chambers, causing catastrophic hydraulic lock. Too small, and the droplets evaporated before providing adequate cooling. The pump had to maintain consistent pressure across widely varying altitudes and temperatures. Failure of the pump while the engine was running at high boost pressure would cause immediate and catastrophic engine destruction within seconds, as detonation tore the internal components apart. The system needed absolute reliability despite the brutal vibration environment of a radial engine operating at maximum power. Pratt & Whitney engineers spent thousands of hours testing and refining every component. By early 1943, they had developed a water injection system reliable enough for combat operations. The system allowed boost pressure increases that raised engine output from 2,000 horsepower at military power to 2,200 horsepower at war emergency power, a 10% increase. This might seem modest, but the effect on aircraft performance was dramatic and immediately noticeable to pilots. At sea level, war emergency power increased the F6F's climb rate by approximately 500 feet per minute, from 2,300 to 2,800 feet per minute. At 10,000 feet, the improvement was equally significant, from 2,360 feet per minute to 2,800 feet per minute. Maximum speed increased by 25 to 30 miles per hour, below 23,000 feet altitude. These improvements brought the F6F climb performance nearly equal to the zero below 14,000 feet and decisively superior at all higher altitudes. The tactical implications were profound and immediately recognized by experienced combat pilots, who understood viscerally how critical climb rate was to survival and victory. With war emergency power available, American pilots could compete with Japanese fighters in climbing engagements from nearly equal starting positions. They could overcome altitude disadvantages of several thousand feet in just minutes of sustained climbing. They could accelerate more rapidly in dives and zoom climbs, extending or closing range at will. But the system came with significant limitations and operational restrictions that pilots had to understand completely and follow absolutely, or face catastrophic consequences. The water-methanol mixture supply was limited to approximately 12 gallons. At the consumption rate required for war emergency power, this provided approximately 12 minutes of operation under ideal conditions. In practice, the mixture was consumed more rapidly, providing perhaps 8 to 10 minutes of actual war emergency power operation, depending on altitude and engine RPM. The Navy established strict operational limits for war emergency power usage. Continuous operation was not to exceed 5 minutes under any circumstances. Engine limitations, not fluid supply, imposed this restriction. Even with water injection cooling, the extreme boost pressure and combustion temperatures caused accelerated wear on pistons, cylinders, and other internal components. Extended operation risked catastrophic mechanical failure from overheating or detonation. After 5 minutes, the pilot was required to reduce power to military power or below to allow the engine to cool. The pilot's operational procedure was specific and demanding. Before activating war emergency power, the pilot had to verify the ADI fluid quantity gauge showed adequate supply. An empty or nearly empty tank meant attempting war emergency power would destroy the engine within seconds. The pilot then activated the ADI pump using a switch on the instrument panel. This pump needed approximately 15 to 30 seconds to pressurize the system and ensure fluid was flowing to the injection nozzle before high boost pressure was applied. Only after confirming system activation could the pilot advance the throttle past the detent or break the restraining wire that prevented accidental engagement. A small indicator light on the panel confirmed the system was operating. If this light extinguished during war emergency power operation, indicating pump failure or fluid exhaustion, the pilot had to reduce throttle immediately to military power within seconds to prevent engine destruction. The supercharger settings added another layer of complexity to power management. The R-2800 engine featured a 2-speed supercharger with neutral, low ratio, and high ratio settings. At low altitudes, up to approximately 7,000 feet, the supercharger operated in neutral position, providing minimal boost. Between 7,000 and approximately 22,000 feet, the pilot shifted to low ratio for increased boost pressure to compensate for thinner air. Above 22,000 feet, high ratio provided maximum boost for high-altitude operation. Shifting supercharger ratios required specific throttle manipulation to prevent overboosting the engine during the transition. To shift from neutral to low or from low to high, the pilot had to reduce throttle momentarily, engage the new ratio, then smoothly advance throttle back to the desired setting. The pilot's manual warned explicitly never to close the throttle completely or make abrupt throttle movements while operating in low or high ratio supercharger settings, as this could cause backfire or flame propagation through the induction system. War emergency power was available in all supercharger settings, but the performance gains varied with altitude. At low altitude, in a neutral supercharger, war emergency power provided maximum benefit because the engine was not already operating at high boost pressure. At high altitude, in the high ratio supercharger, the engine was already highly boosted, so war emergency power provided less additional benefit, but still significant performance improvement. If the water-methanol mixture was exhausted while operating war emergency power in low or high supercharger ratio, the auxiliary stage pressure regulator would automatically reduce manifold pressure to safe military power limits, protecting the engine. However, this protection did not function in a neutral supercharger setting. If the mixture exhausted while operating war emergency power in neutral ratio below 7,000 feet altitude, the result would be serious engine damage or total failure within seconds unless the pilot immediately reduced throttle to military power. The pilot also had to remember to deactivate the ADI pump after reducing power from war emergency power operation. The pump was not designed to run dry. Operating the pump with an empty tank would damage the pump through cavitation and overheating. In the chaos of combat, with multiple tasks demanding attention simultaneously, forgetting this step was easy and could leave the pilot without war emergency power capability for future emergencies. Despite these complexities and limitations, experienced pilots quickly mastered war emergency power management and incorporated it seamlessly into their combat procedures. The performance advantage was simply too significant to ignore. Pilots who used war emergency power effectively survived encounters they would otherwise have lost. They achieved victories that would otherwise have been impossible. They reported the system saved their lives repeatedly in desperate situations where conventional power was insufficient. The first F6F Hellcats equipped with the water injection system began reaching combat squadrons in the Pacific in April 1944. The F6F featured several improvements over the F6F, including a redesigned engine cowling for better cooling, an integral bulletproof windscreen replacing the separate armored glass plate, revised ailerons with spring tabs for reduced control forces, and strengthened tail surfaces. But the most significant change was the Pratt Whitney R-280010W engine, where the W specifically designated water injection capability. Late production F6F seconds had also received the water injection-equipped R-280010W engine beginning in early 1944, so both F6F and F6F variants operated side by side in combat squadrons with identical power capabilities. Pilots transitioning from older F6F seconds without water injection to the newer aircraft immediately noticed the dramatic performance difference. The new Hellcats felt substantially more powerful, climbed noticeably faster, and accelerated more aggressively. Initial training and familiarization with war emergency power emphasized caution and strict adherence to the operational limitations. Instructors at operational training units stressed repeatedly that war emergency power was for genuine emergencies only, not routine operations. The 5-minute continuous operation limit was absolute and non-negotiable. Exceeding this limit risked engine failure that could kill the pilot far from any friendly ship or airfield. The consequences of improper use were immediate and catastrophic. But as pilots gained combat experience with the system, their confidence grew, and their tactical employment became progressively more aggressive and creative. They discovered that war emergency power could be used not just defensively to escape danger, but offensively to gain decisive advantages in engagements. The psychological impact on both American and Japanese pilots was significant and measurable through combat reports and post-action interviews. American pilots found that the sudden acceleration and climb capability broke the enemy's mental model of what Hellcats could do. Japanese pilots who had fought F6F seconds without water injection expected specific performance limitations based on their experience. When an F6F suddenly accelerated or climbed at rates 30% higher than expected, Japanese pilots were forced to recalculate angles, closure rates, and escape possibilities in real time during the stress of combat. This cognitive overload created opportunities American pilots exploited ruthlessly. The improved climb rate was particularly valuable in the most common combat scenario. American combat air patrols typically maintained station at 15,000 to 20,000 feet altitude to provide adequate time to intercept Japanese raids detected by radar. Japanese formations approaching at altitudes between 10,000 and 15,000 feet gave the defenders several minutes to close the distance and engage before the enemy reached the fleet. In these engagements, American fighters dove from their patrol altitude to build speed, then zoomed back up to the enemy's altitude or higher to gain position advantage. The zoom climb was critical because it determined whether the American fighters reached advantageous firing position or were forced to engage from disadvantaged positions below and behind the enemy. War emergency power during the zoom climb made the difference between gaining position or missing the opportunity entirely. Pilots learned to time their war emergency power usage precisely. Activate during the zoom climb after the initial dive to maximize altitude gain. Achieve position above and behind the enemy formation. Deactivate war emergency power once position was achieved to conserve fluid and engine life. Make the diving attack using gravity and built-up speed. Use war emergency power again if needed during the escape and repositioning for another attack. This cycle could be repeated multiple times within a single engagement, each usage consuming roughly 1 to 2 minutes of the available supply. Commander David McCampbell's experience on November 11, 1944, demonstrated the system's effectiveness in overcoming significant altitude disadvantages. McCampbell was leading 16 F6F Hellcats from Air Group 15 on an escort mission for dive bombers and torpedo bombers, striking Japanese convoy traffic near Ormoc Bay on the western coast of Leyte Island in the Philippines. The Japanese were desperately trying to reinforce their garrison at Ormoc, with troops and supplies brought by fast destroyers and transport ships from bases to the west. American air power was systematically destroying these convoys, strangling the Japanese defense. The Japanese committed significant fighter strength to defend these critical supply operations. American intelligence estimated approximately 60 to 80 Japanese fighters operating from airfields in the central Philippines. As McCampbell's strike group approached the target area at 14,000 feet, the escorts spotted approximately 20 Japanese fighters climbing from below to intercept. The enemy aircraft included Nakajima Ki-43 Oscars, Nakajima Ki-44 Tojos, and some Mitsubishi A6M0s. The Oscars, in particular, were climbing aggressively toward the American bombers, attempting to break up the attack before the bombers could reach their release points over the convoy. McCampbell assessed the situation instantly with the experience of hundreds of combat hours and 28 aerial victories already to his credit. The Japanese fighters held a 3,000-foot altitude advantage, positioned at 17,000 feet, while the American escorts were at 14,000 feet. The bombers behind and below McCampbell's fighters were vulnerable during their attack runs when speed decreased and maneuvering was restricted. Standard procedure was to maintain position and rely on the bombers' defensive gunnery combined with fighter cover to drive off attackers. But McCampbell recognized an opportunity. If he could gain altitude rapidly enough to engage the climbing Japanese fighters before they reached the bombers, he could disrupt their attack and force them into defensive, maneuvering that would prevent coordinated strikes. The 3,000-foot deficit seemed insurmountable in the time available. A standard rate of climb would require several minutes to close that gap, time the bombers did not have. McCampbell activated his ADI pump, verified the system pressurization on his gauges, and advanced his throttle firmly past the detent into war emergency power. The Hellcat surged forward with immediate and dramatic acceleration. The manifold pressure gauge indicated 48 inches of mercury, 6 inches higher than military power. The engine's deep roar intensified to a higher-pitched howl as 18 cylinders consumed fuel and water methanol mixture at maximum sustainable rate. The rate of climb indicator stabilized at 2,900 feet per minute. At this climb rate, McCampbell would gain 3,000 feet in approximately 60 seconds. He called out his intention over the radio to his wingmen who followed his example, all 16. Hellcats climbing at war emergency power toward the enemy fighters above. The Japanese pilots, expecting a more gradual American response, continued their own climb toward the bombers. They maintained their formation, conserving energy and position discipline for their planned, coordinated attack on the vulnerable torpedo bombers. By the time they recognized the American fighters were climbing at unprecedented rates, McCampbell's division had already closed half the altitude gap. In 1 minute and 30 seconds of sustained war emergency power climbing, McCampbell's Hellcats reached the same altitude as the lead Japanese formation. In another 30 seconds, they had an altitude advantage. The positions were reversed. The Japanese pilots, suddenly finding American fighters above them instead of below, broke formation to maneuver defensively. The coordinated attack on the bombers dissolved into individual survival struggles. McCampbell reported in his post-mission action report that the F6F with war emergency power was able to overcome a 3,000-foot altitude disadvantage and catch Oscar fighters in approximately 3 minutes at their best altitude of 11,000 feet. This represented climb performance equal to or better than the Japanese fighters achieved, a decisive tactical advantage that reversed the typical dynamic where Japanese fighters held climb superiority. The engagement that followed demonstrated how altitude advantage translated directly into tactical dominance. McCampbell's Hellcats dove on the disorganized Japanese formations, achieving firing solutions before the enemy could effectively respond. Air Group 15 claimed 10 confirmed Japanese fighters destroyed during the engagement with no American losses. The bombers completed their attack on the convoy unmolested, sinking several transport ships. The tactical lesson circulated rapidly through Navy fighter squadrons. War emergency power could overcome altitude disadvantages measured in thousands of feet given adequate time and fuel supply. Pilots began planning their intercepts to include war emergency power as a standard component rather than emergency reserve. Flight leaders briefed their divisions on specific procedures for coordinated war emergency power usage to maximize the entire formation's climb performance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The system proved equally valuable in desperate defensive situations where pilots faced overwhelming numerical odds or disadvantageous tactical positions. The incident involving Lieutenant Ira Kepford of VF-17 on February 19, 1944, though he was flying an F4U Corsair rather than a Hellcat, illustrated principles that applied equally to F6F pilots using similar water injection systems. Kepford found himself alone at low altitude, with 4 Japanese fighters pursuing him after he had destroyed a Japanese seaplane. He attempted to outrun the pursuers, but was cornered against mountainous terrain with limited fuel. The water injection system in his Corsair worked fitfully, providing intermittent boost that allowed him to maintain just enough speed to prevent the Japanese fighters from achieving firing position. When one pursuer attempted to cut inside his turn to get a shooting angle, the enemy pilot misjudged altitude and struck his wing into the water, destroying himself without Kepford firing a shot. The incident demonstrated that even inconsistent war emergency power could provide enough performance advantage to survive situations that would otherwise be fatal. Kepford's survival vindicated the investment in water injection technology and reinforced to pilots that the system worked when needed most. Many pilots later credited their survival to similar use of emergency power in desperate circumstances. The Japanese never developed comparable water injection systems for their frontline fighters during World War II. This absence was not due to lack of engineering capability or understanding of the principles. Japanese engineers were fully aware of water injection technology. German allies had shared technical information about their systems. But Japan lacked the industrial capacity to implement such systems across their fighter production, while simultaneously dealing with catastrophic material shortages and disrupted manufacturing. By 1944, American submarine operations had effectively cut Japan's maritime supply lines, strangling the flow of raw materials, including petroleum products, aluminum, and specialized chemicals. The methanol required for water injection systems was a petroleum derivative that Japan could not produce in sufficient quantities. The specialized pumps, pressure regulators, and injection nozzles required precision manufacturing capabilities that Japanese industry struggled to maintain as bombing intensified and skilled workers were drafted into military service. Japanese fighter development during 1944 and 45 focused on incremental improvements to existing designs rather than implementing complex new systems. The A6M50 added slightly thicker wing skins to allow higher diving speeds and minimal armor protection behind the pilot's seat. The Kawanishi N-1KJ Shiden incorporated powerful engines and heavy armament, but sacrificed the maneuverability that had been Japan's primary tactical advantage. The Mitsubishi J-2M Raiden emphasized high-altitude interception for homeland defense against B-29 bombers. None of these aircraft received water injection systems. They fought with conventional, normally aspirated or supercharged engines operating at military power as their maximum sustainable output. Against American fighters equipped with war emergency power, Japanese pilots found themselves consistently disadvantaged in climb rate and acceleration. The performance gap that water injection created became one more factor, contributing to the progressive deterioration of Japanese air power effectiveness. The kill ratios tell the story of accelerating Japanese defeat. In early 1943, when the first F6F Hellcats without water injection entered combat, the kill ratio was approximately 3-1 in favor of American forces. Still significant, but reflecting that Japanese pilots and aircraft remained dangerous adversaries. By mid-1944, after F6F seconds with water injection had replaced most older aircraft in frontline squadrons, the kill ratio had increased to approximately 10-1 in favor of American forces. The Battle of the Philippine Sea in June 1944, nicknamed the Great Marianas Turkey Shoot by American pilots, demonstrated American fighter dominance decisively. On June 19, 1944, Japanese naval aviation launched approximately 373 carrier aircraft in multiple waves against American Task Force 58. The Americans destroyed approximately 300 of these aircraft in a single day of combat. American losses totaled approximately 30 aircraft, achieving a 10-1 kill ratio. Commander McCampbell participated prominently in this battle, flying his F6F Hellcat and using war emergency power repeatedly during multiple intercepts. He shot down 5 Japanese D-4Y Judy dive bombers during a morning patrol, achieving ace-in-a-day status with 5 victories in a single mission. During an afternoon sortie, he shot down 2 A6M0 fighters, bringing his total for the day to 7 confirmed victories. McCampbell used war emergency power during the climbing intercepts and zoom climbs that positioned him advantageously for these attacks. The Turkey Shoot marked a fundamental turning point, where American technological and numerical superiority combined with tactical excellence to achieve air supremacy that Japan could never again challenge effectively. Water injection was only one component of this superiority, but it was significant enough that pilots noticed its absence on the rare occasions they flew older F6F seconds without the system. Pilots who had to revert to aircraft without water injection for any reason, such as battle damage to their assigned aircraft or temporary assignment to squadrons equipped with older models, reported feeling distinctly disadvantaged. They described the aircraft as feeling sluggish and underpowered compared to what they had become accustomed to. The psychology of this perception was significant. Pilots who believed their aircraft was superior flew more aggressively and took calculated risks they would otherwise avoid. Confidence translated directly into combat effectiveness. The water injection system required remarkably little maintenance under combat conditions. The components were robust and designed for the harsh environment of carrier operations where salt spray, temperature extremes, and constant vibration challenged every system. The ADI tank needed refilling after each mission where war emergency power had been used. Ground crews maintained supplies of the water methanol mixture in 55-gallon drums on the hangar deck of carriers and at island-based airfields. Refilling was a simple procedure requiring approximately 15 minutes. Ground crew attached a hand pump to the aircraft's fill port located on the fuselage side, pumped the mixture from the drum into the tank, and verified the quantity gauge indicated full. The pump itself required periodic inspection and maintenance, primarily checking electrical connections and verifying pressure output, but proved remarkably reliable in service. The injection nozzles occasionally required cleaning to remove carbon deposits that could partially block the spray pattern, but this maintenance could be performed quickly during routine engine inspections. The steel pressure lines were inspected regularly for leaks or damage, but rarely required replacement. The system's simplicity and reliability meant aircraft availability rates remained high. Squadrons rarely had aircraft grounded specifically due to water injection system failures. By 1945, water injection had become so standard and routine that new pilots training in the United States practiced with war emergency power during advanced tactical training. The mystique and caution that surrounded the system initially had dissipated. Pilots learned to use it as naturally as any other aircraft system, integrating it seamlessly into their tactical procedures. The final months of the Pacific War saw F6F Hellcats with water injection dominating Japanese air power so completely that encountering organized fighter opposition became increasingly rare. The Battle of Okinawa from April through June 1945 demonstrated the extent of Japanese desperation. Unable to contest American air superiority through conventional air combat, Japan resorted to kamikaze suicide attacks, where pilots deliberately crashed their aircraft into American ships. F6F pilots flew thousands of combat air patrol missions over the invasion fleet at Okinawa, intercepting kamikaze attacks before they reached the ships. War emergency power allowed rapid response to radar vectoring, climbing quickly to intercept altitude and positioning to attack approaching raids. The Hellcats destroyed hundreds of Japanese aircraft attempting kamikaze attacks, though many still penetrated to strike American ships with devastating effect. The statistics for the F6F Hellcat throughout the war are extraordinary and unprecedented. Total Hellcat production reached 12,272 aircraft, all manufactured at Grumman's Bethpage, Long Island facility. These aircraft were credited with destroying 5,163 Japanese aircraft in aerial combat, approximately half of all Navy and Marine Corps aerial victories in the Pacific. An additional 3,500 Japanese aircraft were destroyed on the ground by strafing Hellcats. The Hellcats' kill ratio reached approximately 19-1 by the war's end, meaning for every Hellcat lost to Japanese fighters, 19 Japanese aircraft were destroyed. This ratio was the best achieved by any American fighter aircraft during World War II. The F6F produced 307 fighter aces, pilots who achieved 5 or more aerial victories. This was more aces than any other American aircraft type created. Commander David McCampbell finished the war as the United States Navy's all-time leading ace with 34 confirmed aerial victories, all achieved while flying F6F Hellcats during his single combat tour from April to November 1944 with Air Group 15. He was the only American fighter pilot to achieve ace-in-a-day status twice, with 5 or more victories in a single mission on 2 separate occasions. His Medal of Honor citation specifically noted his leadership and tactical excellence during the First and Second Battles of the Philippine Sea, where his aggressive use of altitude advantage and energy tactics, enabled by war emergency power, contributed decisively to his success. Lieutenant Alexander Vrasiu of VF-6 and VF-16 achieved 19 victories flying Hellcats, making him one of the Navy's top aces. On June 19, 1944, during the Turkey shoot, Vrasiu shot down 6 Japanese aircraft in a single 8-minute mission, one of the most remarkable single-mission performances of the war. He used war emergency power to climb rapidly to interception altitude, achieving perfect position above and behind a formation of Japanese Judy dive bombers before they could reach the American fleet. The list of Hellcat aces includes dozens of pilots whose names became legendary in naval aviation. Lieutenant Cecil Harris, Lieutenant Patrick Fleming, Lieutenant Eugene Valencia, each with more than 20 victories. Hundreds more pilots achieved multiple victories without reaching ace status, but contributed equally to American air superiority. They all shared one common experience. They had flown the Hellcat with and without water injection, and they universally preferred the enhanced performance that war emergency power provided. After the war ended in August 1945, thousands of Hellcats were declared surplus and removed from service rapidly as the Navy demobilized. Some were sold to Allied nations, including France and Uruguay, where they served for years. Many were simply pushed overboard from carrier decks in mass disposals to make room for jet aircraft. Some were preserved in museums or purchased by private collectors. A few remain airworthy today, maintained by dedicated warbird enthusiasts who keep these historic aircraft flying for air shows and demonstrations. Pilots who fly restored F6F Hellcats report that the water injection system has usually been disabled or removed for safety and maintenance reasons. The systems are complex to maintain properly. The water-methanol mixture is difficult to source in appropriate composition, and the risk of catastrophic engine damage from system malfunction is unacceptable in an irreplaceable historic aircraft. Modern pilots flying these warbirds experience the Hellcat at military power settings, impressive enough with 2,000 horsepower available, but missing the extra 200 horsepower surge that combat pilots relied upon. The handful of restored Hellcats that retain functional water injection systems are maintained by organizations with extensive warbird expertise and deep financial resources. Properly demonstrated, war emergency power still produces the dramatic acceleration and climb performance that combat pilots experienced 8 decades ago. Airshow spectators who witness these demonstrations see and hear the visible difference as the pilot advances the throttle past the detent, and the engine note changes from a powerful roar to an urgent howl. The engineering principles that made water injection effective in 1944 remain valid today, though the technology has evolved substantially. Modern turbocharged aircraft engines sometimes use water-methanol injection for similar cooling and detonation suppression purposes. High-performance military aircraft use even more sophisticated systems, including afterburners that inject additional fuel directly into the exhaust stream for short-duration thrust increases. The fundamental concept of sacrificing engine life for temporary performance gains in critical situations remains unchanged. But the F6F Hellcat's water injection system occupies a unique place in aviation history as one of the most successful implementations of this technology. Deployed at scale across thousands of aircraft, used routinely by hundreds of pilots in actual combat, and proven effective through measurable combat results. The system contributed significantly to American victory in the Pacific by providing American pilots with performance advantages that Japanese pilots could not match. The title's suggestion of an illegal throttle trick is historical hyperbole rather than fact. War emergency power was neither illegal nor a trick. It was an officially sanctioned, carefully engineered, and extensively tested system built into production aircraft with complete Navy approval and endorsement. The limitations on its use were operational restrictions intended to prevent engine damage, not legal prohibitions against using the system. Pilots were explicitly trained and authorized to use war emergency power whenever tactical circumstances justified, accepting the risk of accelerated engine wear in exchange for improved performance. Flight manuals, training syllabi, and operational orders all discussed water emergency power openly and provided specific procedures for its employment. There was nothing hidden, secret, or prohibited about advancing the throttle past the detent when circumstances required maximum performance. The psychological perception among some pilots that they were doing something illicit or extreme when breaking the wire or pushing past the throttle stop reflected the system's effectiveness and power, rather than any actual prohibition. The physical action of deliberately breaking a restraint or forcing the throttle past mechanical resistance felt transgressive, like exceeding speed limits or violating safety rules. But this was intentional design to prevent accidental activation, not indication that the action was forbidden. Some pilots called it pushing it through the gate or going over the wire, language that carried suggestions of crossing boundaries into dangerous territory. But the danger was to the engine through accelerated wear, not to the pilot through violating regulations. The Navy wanted pilots to use war emergency power when tactically justified. The 5-minute limitation existed to protect the mechanical hardware, not to discourage use. The real story is less dramatic than illegal trick, but more impressive as military technology and operational innovation. American industry designed, produced, and deployed a sophisticated performance enhancement system across thousands of aircraft within approximately 1 year from concept to combat deployment. American pilots learned to use this system effectively, integrating it into tactical doctrine and combat procedures. The resulting performance advantage contributed measurably to air superiority that strangled Japanese power projection and enabled American advance across the Pacific. This achievement represented the industrial mobilization, technological innovation, and tactical adaptation that characterized American success in World War II more broadly. The United States possessed sufficient industrial capacity to add complex systems like water injection to aircraft production without compromising output volumes. American pilots received sufficient training to master complex engine management procedures without overwhelming their cognitive capacity during combat stress. American tactical doctrine evolved continuously to incorporate new capabilities as they became available. Japan could not match this combination of industrial capacity, technological innovation, and tactical flexibility. Japanese aircraft designers understood water injection principles and could have developed similar systems if resources permitted. But Japan's shrinking industrial capacity, material shortages, and disrupted production meant that even proven technologies often could not be implemented at scale. The gap between what Japanese engineers could design and what Japanese industry could produce widened catastrophically during 1944 and 45. The F6F Hellcat with war emergency power represented one element of this growing capability gap. American pilots flying these aircraft enjoyed performance margins that made Japanese fighters progressively less dangerous. The Zero that had seemed invincible in 1942 became increasingly obsolete by 1944 as American fighters gained advantages in speed, climb rate, armor protection, and firepower. Water injection was only one factor among many, but it was significant enough that pilots noticed and valued it. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.